So there's this video of the Tesla Cybertruck ascending a hill, and it's got a lot of people very excited and drawing some incorrect conclusions. So in this video I'm going to be analysing exactly what's going on and taking a look at it relative to the Rivian and F-150, and see what conclusions we can really draw from it. So let's take a look at a reference vehicle, a Bronco, trying to get up, and it's failing, but not because of the car, because of incorrect driving technique. The guy on the video knows exactly what he's doing and is trying to communicate to the driver, who is applying power at that point, which is exactly the wrong point. I'll talk more about that in a second. Poor old Steve getting out of the way there.
Bring your tail towards me a little bit.
And now is being directed to do the right thing, which is come back, not too far. I don't want to get those front wheels over the ledge. Mr. Video Guy knows what it's talking about. He doesn't need to go that far, just needs to apply just enough momentum here to get up and over. Once he's done that, it's a pretty easy climb for that vehicle with four-wheel drive, good suspension and tall diameter tyres. That's the important thing. It just goes up and over that with no problem at all. Let's look at what the Bronco driver is doing. There's the rock ledge, there's the wheel, and there's a distance between the wheel and the rock ledge. So what he's doing is he's applying moderate throttle, and that moderate throttle is enough to move the vehicle forwards, but when the wheel gets to that ledge, that throttle's not enough to get up over the ledge. So at that point, the driver realizes it and increases the revs, and all that does is, as you can see, spin the wheel, not the correct way to do it. Now if we go back and then we apply a little bit more throttle, so we have a little bit more speed, then we've just got enough to get over the top, and that's what you see happen when the driver is finally successful. So this is what I mean using a radio controlled car as an example. It's the Suzuki. Now in this case we're just going to apply a moderate amount of throttle. We're just going to come up to a ledge, and then therefore the vehicle stopped. I just need to apply more throttle and the car gets over it. Now that works for a smaller ledge, and it works again for the back axle. I'd come to a halt, apply more power, and the car gets up and over. Over here, it sort of works as well. But when I get to this point, I can come to a stop and I can apply as much power as I want, nothing happens. And that's what was happening with the Bronco driver. So again, I go back. This is what the Bronco driver is doing. Applying a little bit of power, gets to that point. Once it gets to that point, it goes more power, but it's too late. This is what you've got to do. You've got to go back to the point where you've got a good run up, wheels are almost going to go over the edge but not quite. Then apply a little bit of power earlier like this, and then you're up and over. It's not more power, it's just power a little bit earlier using momentum to get up and over. Now that point about power and momentum, so we've got this distance between the wheel and when it's going to get over that ledge. What you want to do is apply your power at this point over here, not wait till you get to the point where the wheel is trying to get up over the ledge and then apply power. That's going to be too late. Now it's also interesting to look at the track. There's two things that we can learn from it. One, we can see this rubber mark here, and that is witness to the fact that people have spun tyres on it. So as you're coming up to something like this, you can look for witness marks like that, and that's what I term track forensics. You can learn about what other people have done. Another good track forensic might be scraping of differential marks in the centre of the track indicating running out of clearance. Now you don't necessarily know which cars made those marks or tracks, but it does give you an idea. Now the other point over here is that this is a consistent ledge, but there's this extra rock here, and that actually has an interesting effect. So I've replicated this. It's not to scale, but approximately. That's what the wheel looks like on the left hand side, and that's what it looks like on the right hand side with that rock I've put in purple there, and the equivalent angle is much less here compared to that. So when you put your wheel on that right hand side, that right hand wheel is going to have an easier time rolling up over a shallower gradient. This shot does give us a good idea of what the ledge is like. So again, we can see here the witness mark of the wheel spin. That tells us something. We can see over here that nice little ledge which makes life a lot easier to get up and over. If you use that, you will be aware that as one wheel comes up over here, the left wheel might be in the air a little bit, but with brake traction control or cross-axle differential locks, or even just good suspension flex, that won't be a problem, and the whole vehicle will be lifted up. So generally, I would definitely look to put my right wheel on that ledge just to start lifting the vehicle up, as opposed to try and avoid it. Now also over here there's another ledge, and I think that becomes significant later on. Now we've got the Rivian EV four-wheel drive driven by a more skilled driver, and carefully using the rock ledge on the right hand side there with the back and I think the front wheel to lessen the angle. Now the car's going straight ahead, mark of a good driver there, and then it's turning once the back wheels are over, which is great. Now that front right wheel is going to get a little bit unloaded there, as you can see, so briefly spins and keeps going, and that's really great off-road engineering by Rivian, just to detect and arrest that wheel spin and send a torque to where it needs to go. Same sort of deal here, and it same's happened there. Now I think that a touch more momentum would have made the climb just a little bit easier. You see it's coming to a complete stop here, and that's not great for off-road driving. You want to keep even a tiny bit of momentum going, but you can see here it is, front right is spinning and the car slews around a little bit, so that's not ideal. A touch more momentum would have solved that, but this climb, testament to how good the Rivian is off-road, I feel. And here I think that's the rear left spinning and the car slews sideways, but immediately the car detects what's happening, sends torque to where it needs to go, and up it comes. And if I was calibrating that, I'd have the front wheels be pulling more, and I'd reduce torque to the wheel that's spinning. Now the Rivian driver I think is being quite skillful here, because that rock we talked about earlier on, I think his back wheel is just, or her back wheel is just over the top of that. And that is quite skillful driving, just to look at the track and precisely place your wheels exactly where they need to be. Now this is where the Rivian does really well. So we've lost traction, or we need more torque on the right wheels over here, and what's happening is that the vehicle reacts to that very, very quickly and does in fact send a torque over to the right front wheel, and I'm not sure which one of the backs needs it the most, but it's actually quite a quick reactive system. I'm quite impressed with Rivian's engineering there, the way that the system figures out what torque needs to go to which wheel and sends it appropriately, and that is going to be a massive advantage electric vehicles have over internal combustion engines. If you can do individual wheel drive, you have one motor at each wheel, as some Rivians in fact do, and you instantly and precisely send exactly the right amount of torque to each wheel. You can't really do that in an ICE vehicle. You've got differentials, you've got brakes, you've got torsion diffs, you've got LSDs, you've got all sorts of these mechanical devices which are simply not as good as electric individual wheel drive, and I've got a specialist video about that. And here's a rear view, so the back right wheel is spinning. Now you can see that the brakes are on and off. That is surprising. Going up a hill that steep, I would not expect the brakes to be used. I would want a mode on that vehicle which is so slow that I don't need to use the brakes and jump from brake to accelerator.
Back up.
And that's what you'd get, let's say, Wrangler Rubicon of a 1:80 or 80:1 crawl ratio. But still an impressive engineering feat from Rivian to be able to do that like that and distribute the torque where it needs to go. Now we come to the Cybertruck, which is not driven well. Now it's a test vehicle, so it could be intentionally driven badly. You do that during testing, but nevertheless it is not a good driving demonstration, because we've got that right rear wheel, which almost looks to be rear wheel steer as well, I can't quite see it, to be spinning, and that can be solved easily just by a fraction more momentum and a better line. And I'd also suggest that Tesla's traction control needs a bit of calibration. So the car comes up here, up and over, and it's going pretty much okay here. Then the driver just makes this abrupt turn, and it's going very fast, and it allows it roll back. This is terrible driving. This point here, you can just contrast that with the Rivian. The Tesla's traction control systems really need to divert torque to the appropriate wheel, and the Rivian did that beautifully, and the Tesla absolutely did not. But let's be really clear, this is an early prototype vehicle. Now in this close-up you can see the rear wheel steering happening as the front wheels turn right, the rear wheels turn inwards. That will open up a new dimension of capability and manoeuvrability for electric vehicles, more so than ICE vehicles. It's easier to put in there. You can also see that right rear wheel spinning quite a bit, and again that's saying the traction control calibration needs improvement. The Cybertruck has real problems here. Now, it's not really being driven very well. The driver is on and off the throttle. Now, that could mean poor driving, but it could also mean that the throttle response is poorly calibrated. In situations like this, you don't want a hair trigger response, you want a soft throttle response, so you can more precisely meter out the torque. When you're bouncing around, if your foot is on the side of the throttle, then it doesn't accidentally put in a throttle input. One way to mitigate that is to put your foot against the side of the sidewall, and then that helps stop bouncing around if your car lets you do it. Anyway, you can see that the back end of the Cybertruck has slid round here, and the driver's had to apply some left-hand lock to keep the vehicle straight. So that's telling me that the Cybertruck's ability to distribute torque correctly is not as good as the Rivian or the F-150. Driver and line have a bit to do with that as well. What it should be doing in this situation is saying, okay, this wheel needs more torque than the other wheels, so let's deprioritize the back, let's put a bit more torque onto the front wheels, and let's bring it up and over as opposed to pivot the car around, as we saw was the case in the Rivian. Now, of course, this is not a production vehicle, it's not out yet, so they are still calibrating. It's a test vehicle, whereas the Rivian is a production vehicle, so it's not really a fair comparison, but nevertheless we can still learn something. Now we've got the Ford F-150 Lightning, and let's have a look and see how that does. Now, taking a nice wide line, or fairly wide line, to try and line up initially, and you can see it's got over the first part quite well. Wheelbase makes a big difference in these situations as well. Sometimes a long wheelbase is good, sometimes it's not so good. And you can see that the driver's picking a good line here. Again, coming to a halt, and that's not ideal. You just want to keep your momentum rolling even just a little bit. Taking a different line to the Tesla, going out to the left as opposed to out to the right. And coming up here. And that's pulled, I don't know if I'd put that right wheel over that rock ledge. And you can see the back of the car skews round. The Rivian did that better. The Ford didn't seem to distribute torque to the front wheels as it should in that situation, which you can do with electric vehicles. You can't do that quite so easily with an internal combustion engine. So a really important part of off-road engineering is to make sure that of the four wheels on a vehicle, you have exactly the right amount of torque or turning force going to each wheel at any given time, and that's going to constantly vary depending on the terrain. And that's what we're seeing with all of these vehicles now. I'm going to simulate what's happening on that ledge. So we're just going to put this left wheel up against this ledge here. I'm going to apply the throttle. You can see the car skew sideways. Now the reason for that is that the front left wheel needs more torque than the other three wheels, and it's not getting it for reasons of differentials which I won't go into now. Now the Rivian seemed to react pretty quickly to that and increase the torque on the front left wheel, and the others, Ford 150 a bit less quickly, and the Cybertruck really not so much at all. Now we can actually fix this with something called cross-axle locking differentials, which I'm going to engage now. There they go in, and that will in effect increase the torque to that front left wheel, and we can get up and over. Now those vehicles probably don't use cross-axle locking differentials. They, in the case of the Rivian, I think it's got individual wheel drive where each wheel is driven by its own individual motor, and that's probably better than locking differentials. We can have that discussion if you want in the comments, but either way the concept is it's engineering to get exactly each of those four wheels the precise amount of torque they need at any given point for maximum off-road traction and efficiency. Now let's take a look at wheelbases. So this is a scale diagram of the Rivian, the F-150 and the Cybertruck, all different wheelbases. Now I'm going to put that line through the centre. Now if we put this yellow obstacle, I'm going to set it so that both wheels on the Rivian have to get over these little obstacles. Now that is really bad for the Rivian because both wheels have to try and get up over these chock things at the same time. That's really going to be quite hard work for it. Now if we take that exact same obstacle and we apply it to the F-150, the F-150 has got a longer wheelbase, and therefore it only has to get its front wheel over the top, and its back wheel doesn't have to deal with getting over that obstacle there, and the same is true of the Cybertruck. So in this particular case, the Rivian would be disadvantaged by its wheelbase, but we can of course turn that around, and we're going to make the second obstacle exactly the wrong sort of length for the F-150 and the Cybertruck, and you can see that the Rivian, its back wheels are pretty much up and over, so it would actually deal better with that particular obstacle. Now in four-wheel driving terms, sometimes the long wheelbase is good, Sometimes the long wheelbase is bad. It's really dependent, and ideally you'd want to vary your wheelbase almost every 1 metre on the trail, but you can't do that. So you can't say long wheelbase is always better, short wheelbase is always better. It's really very situation dependent. Now, tyre diameter is also really important as well. We've got 2 identical obstacles here, and you can see that we've got a small tyre and a large tyre, and here's the effective angle. You can see that the effective angle here is much shallower than the effective angle there, and that's why taller tyres work better off-road, particularly going up those rock ledges. The taller the tyre, the shallower the effective angle, and the better it is to roll over the top of it. So a 35-inch tyre is going to do better than a 33-inch tyre, but you know, driver skill and picking a line can make a massive difference. Now we've got an old Jeep, and let's see how this does. Just straight up. Now, you're going to say, oh, well, 1940s, 50s technology is better, right? Well, no, because there's a couple of things. I reckon this guy probably driven that hill 1,000 times, and also much narrower track, so it can come straight up in the middle and avoid a lot of the obstacles the wider vehicles had to deal with, and came up the fastest of everyone, and momentum does make a difference there. So you can't really go like for like with that climb. So to finish off, here's a look at all 3 vehicles going up the hill at the same time. And remember that the Tesla Cybertruck is not in production, it is a prototype, and it may well have been driven deliberately badly in order to test it. But either way, I think we can say that Rivian have done a really good job engineering their vehicle. Ford, from what I could see there, probably not quite as good, but the F-150 isn't as off-road focused as the Rivian is. Anyway, I hope you found this video useful. If you've got any questions or comments, please use the comment section, and thank you for watching.